in this video, I want to do a tricky kind of example of integration by parts. So this is an example that you should definitely know. It's a classic integration by parts example. And there's a kind of trick to it that's valuable to see once that you can add to your toolbox of things you can do with integration by parts. So the main idea is sometimes you'll have an integral that you start with. You do integration by parts once, and you get to an integral that maybe it's simpler, maybe it's not, and you say, how do I do this integral? And you do integration by parts again. And when you do integration by parts more than once, things simplify. So here's the example. Let's take the integral of e to the x times sine of x dx. Sine of x is a function that doesn't really get more complicated when you differentiate, but it also doesn't really get more complicated when you take an antiderivative. E to the x is the same way. It doesn't get easier when you take a derivative. It doesn't get more complicated when you take an antiderivative. So here we can just kind of pick which part we want to be u and what we want to be dv that's left over. Let's just say that let's let u equal e to the x and dv equals the rest, sine x dx. So then du is just e to the x dx, right, going this way. And dv, well, v should just be any antiderivative of sine, for example, negative cosine of x. So what does integration by parts say? This integral is now equal to u times v. It's e to the x times negative cosine of x minus the integral of v du, negative cosine of x times e to the x dx. Let's clean this up, right? Let's pull this minus sign out here, minus e to the x cosine of x. And now we have a double negative here. So let's write this as plus the integral of e to the x cosine x dx. What we said in the previous videos is that integration by parts sometimes will give you your integral that you started with as a product of two functions plus an integral that's easier to do. This integral, e to the x cosine x, doesn't look any easier than e to the x sine x. In fact, it looks exactly as complicated. So what do we do? Like, how do we do this integral? And there's one really key idea that works great in this example, which is do integration by parts again. So what do I mean? Let's do this integral and let's make similar choices. Let's let u be e to the x. So du is e to the x dx. dv will be everything else. So will be cosine x dx. Well, let me write this more clearly here. dv equals cosine x dx. And then v should be any antiderivative of cosine, like sine of x. All right, so where does that leave us? Well, the first part of our integral doesn't change, this product. We get negative e to the x cosine x plus, now we've applied integration by parts to this second integral, and we get uv e to the x sine x minus the integral of v du. So minus the integral of sine of x times e to the x dx. Okay, so the integral we started with was the integral of e to the x sine of x dx. We did integration by parts twice. And in the end, we don't get an integral that is simpler than the one we started with. It literally is exactly the one that we started with. So here we have integral e to the x sine x. Here we have integral e to the x sine x. So there's this nice trick, which is let's name this integral. Let's call this capital I. So what is capital I equal to, applying integration by parts twice? Let's rewrite this a little. Let's factor out an e to the x. Now we get cosine, sorry, let me put the positive thing first. Sine of x minus cosine of x And what's left is I, minus I. So just to recap, what do we have? We have that this thing we want to understand, I, is equal to e to the x times sine minus cosine. So what does this mean? This means 2 times the integral we want to understand is equal to e to the x sine x minus cosine x. Or said another way, the integral of sine of x times e to the x dx is equal to 1/2 e to the x sine x minus cosine x over 2. So what made this example work is that when you take derivatives and antiderivatives of trig functions up to a plus or minus 1, it just goes sine, cosine, sine, cosine, sine, cosine. There are some negative ones that come in. And when you take antiderivatives of e to the x and derivatives of e to the x, it's just e to the x, e to the x, e to the x, e to the x. So there's sort of this back and forth flipping, where if you do integration by parts twice, you end up with a different way of writing the integral you started with that involves that same integral. So I'll be honest here. We could come up with examples where you have to do integration by parts 3 times or 4 times or 10 times, and it would magically work. There's this related topic called tabular integration that Stewart talks about briefly in the book. You should know this example, and similar techniques will tell you how to do an integral like the integral of e to the x times cosine of x dx. So you should know how to do an example like that one. But you're not going to need to do an example where you have to do integration by parts 6 times. This is the key example to show you that this idea that sometimes you have to do integration by parts more than once, and you get back another expression involving the integral you started with in a way that lets you solve. This is good to know. You can also check that this really does work. Taking the product rule, taking the derivative of this function using the product rule, you should check that it really does give you e to the x times sine of x.